So let's restart screen again and then go back to the which one maybe go segment 6. Okay, let's continue from maybe from this one. Yeah. Okay, do you see it full screen?
Yes,
Okay, good. Right, so let's just continue since from last week's lecture. Okay, so here, if you remember, if we want to have a high purity product, then we have to do some sort of multi-stage distillation. Okay, when we heat it up, when we have the vapor, for example this one uh, here, and we want to cool it down a bit into two phase, then we need energy, right? We need to remove the energy. Okay, we need to cool it down. Okay, so rather to put cooling water in it, let's just put another liquid phase which is a similar stream from the top side, yeah, from the top side. So that's the idea. How, if when you have for example, look at this stage here, when you have a vapor, so this indicate to this arrow, you have 100 of vapor, and then it is mixed with some liquid. Okay, to here, and then you end up with two phases, and it's gonna leave for example the vapor and also the liquid. Okay, so that is the principle. Now, and then if so the multi-stage equilibrium is performed. So this is one stage, two stage, three stage, and so on. So what happens is then if, for example, here up after 9 stages, then we end up with quite purity product, yeah, quite a pure product. Okay, and that is the basic of multi-stage equilibrium, where so it is represented by this one block. Yeah, so one stage is this represented with one block, where the function of stages is first is we need later on in an operational way, we need to design some chamber, or yeah, a chamber, yeah, a chamber, or in this case a stage, that first it can contact between, it allows contact between vapor stream from the bottom and also the liquid from the top. Okay, the vapor from the bottom and also liquid from the top, and then they need to mix together. If you for example, if you bubbled uh, you have a glass of water, and then you put a bubbled maybe a bubbling, yeah, or if you remember, if you know how to make a coffee in a cafe, and then first you have a milk, yeah, and then we put steam inside the milk, if you know that, yes, and then it's gonna fry it up, akan berbuih, yeah, and then there would be a lot of contact between the gas and the vapor and also the liquid. Okay, and after that this should happen very fast, and after that it will leave into an equilibrium until it reach equilibrium between the vapor and the liquid. So where is the vapor? The vapor is this one, and the liquid is this one, and after that we can open uh, the outlet here, or with some ideas, yeah, with some design where the vapor allows to go up and then the liquid goes down. Okay, so that is the function of stages. So this is actually one stage. Okay, and this is also happens in this one, in it is called the rectifying section. Yeah, the rectifying section, or enriching, atau the top side. It's called why it's called the enriching, because it try to enrich the composition of the A. Yeah, if you remember, if this binary component there is A and B, A is more volatile than B, and then we want to have a high purity of A to separate them from B. So it's called the enriching the component of A in this feed stream. Okay, and not all of the A is we need to take it out. Yeah, so some of them we have to put it back into the we have to put it back into the distillation column. Why we have to put it back? Because we need to because we have to uh, that is for also the contact between the liquid and also the vapor, because the liquid goes here and then you have the vapor from there. So there is that is the I mean the contact, yeah, the contact between the liquid from the top, because we need the liquid from the top. Oops. Okay. Okay, and also the vapor from the bottom. Yeah. So that is the enriching and rectifying section. So this is actually there's nothing. Yeah. So this is a stage one. Yeah, it's stage one, and then stage 2, and so on. Okay. All right. So then here you can, if you go back to the previous slide here, or for example here, if it is called the number 9, so then the top one is stage 9. But sometimes commonly we name them with the stage 1 is from the top. So this is stage 1, this one, the second one is the stage 2. Yeah. Okay. So that is the, just to remember or just to remind us about rectifying section. And then how about the bottom here? Okay, so let's go back into the next slide to show you what happened in the bottom section. Yeah, the bottom section is called stripping section. Okay, in the stripping section, again, yeah, so I said to you before that not all of the liquid or not of all of the vapor is taken out from the distillation column. We have to put some of them back into the column in order for them to cool down some of the vapor. Okay, so here that is called the contact, which is denote with I'll go back, put it that. Okay, so this is how so they gonna put back. So if I want to try it again here, yeah, from the stage 1, let's say this one is stage 9 in here. Yeah, so you have the vapor leaving the stage 9. This is the vapor. So the vapor should go back in a way into the liquid using a reflux. Yeah, using reflux, and then it goes to so then this one, the orange is actually here. So this is the liquid, and then it gonna mix with the vapor. Yeah, the mix it with the vapor here, and then to have a mixture here, and then it will leave out the new composition. So then you have another I don't know what's wrong with my pen. It's a little bit bad. So let's try this one. So like that. Okay, and then you do it again until you got the multi-stage equilibrium there. Okay, so one of this step here is called the enriching section. Okay, if you go back here, so what happened with the after here, we can also cool it down into the vapor. We can cool it down into, or maybe we can heat it up, yeah, all the some of the feed into first, maybe, so the liquid is can be, we can heat it up with some vapor, and then we can separate it into two phases again. Okay, and then we, so for example, I can make, oops, what happened with my this one there, so let's try. Give me 1 second. Okay, so okay, yeah, this one is better. Okay, so here, for example, from the feed, you have the feed. Okay, and then you want to have, you have the vapor from downside there, and also you have the vapor, and here there, yeah, this one is your liquid. Okay, so this one is your liquid. Okay, then if you want to strip it, if you want to take some of the A into the vapor phase, what you can do is to put it into another stage of equilibrium. Okay, and then you heat it up. Yeah, you heat it up. So this is the liquid, yeah, and then you heat it up until it goes into two phase. Okay, so how you heat it up? You heat it up with some vapor from down there. Okay, you heat it up there, and then you will leave new phase as well, new phase between the vapor and also the liquid. Yeah, so that is the basic actually. So if you continue here, and then we also can we call it, this one is called stripping, because we add some vapor, and the vapor is from the recycle in the back, which is called reboiler. Okay, so here is the stripping section, where is the vapor, umpan, and then for example, this is the liquid. Yeah, so some of the liquid is still heated up by a reboiler. We call it reboiler because it will heat it up, some of the liquid into a vapor again, and then it goes really slow that way. Okay, so this is called the stripping section. Yeah, so not also all of the product is collected at the bottom product. Some of them need also to be vaporized again by the reboiler to provide the heat. Okay, to provide the heat, and also to supply the vapor goes back into the enriching section. Okay, so then you know the schematic of multi-stage equilibrium, and it is called fractionation. Yeah, in fractionation you have the feed, and also you have the vapor over there. Yeah, the vapor, and all the vapor, because we want to get the product as a usually liquid, then we have to put the condenser on the top of the distillation column. Yeah, but in practically not it's not really at the top. Yeah, if you have a 40 meters distillation column, then of course you can't really put that one, the condenser. Maybe we put a line, yeah, or a pipeline that it will be insulated because it is very hot, and then you have a condenser near the surface. Okay, and then you gonna get the distillate, but not all of them. Some of so we have a valve here, so some goes to the distillate, some of them goes into back into the fractionation column. Yeah, and then it the vapor here, and then always contact intimate with each other in the each stage, and then it is should be goes to the bottom here, but not all of the product should be collected at the bottom product, but some of them need to be put into the reboiler. Okay, and then going back into the fractionation column. All right, okay, so that's the end of the session, and then this will be also repeat it again in the next slide. So then I'm gonna continue to the next slide, and after that, if you have any question, you can also ask. Okay, so now we go to the module 2. This is module 1. Okay. Module 1, module 2. Okay, this one. Stop. Right. Okay, so now we're gonna learn a new module. Yeah, so this is the start where you not really the start. Yeah, you start
Hello, welcome back. Now is the module 2 about distillation.
I still use I'm still using the recording. Wait. Oh, why I have the recording? Okay, put it there. Close it again. Okay, go back. Okay, so here is the so we can start a new module, distillation process, but the typical exam always started from the previous chapter, yeah, about the TXY diagram, about PXY diagram maybe, yeah, or about yeah, some of the for example yeah, how to read the composition. Okay, so this is I took it from the book the Seder and Henley. What is a fractionation column? So this is typical, and then using the mass balance and also some energy balance. Okay, so this is exactly what you're gonna look at the end of the module. So at the end of the module, you need to calculate all of the information in here if we specify the problem. All right, so let's look at this one, yeah, in figure 7.1 here. So this is a distillation of a binary mixture of a benzene and toluene. Okay, so here we have a feed. The feed is at the bubble point liquid. What is a bubble point liquid? What is a bubble point liquid? Anyone want to try? So that is the feed at the bubble point liquid, or because here you have the pressure, so it has at the bubble point liquid at 55 psi, or is it saturated liquid or saturated vapor? Bubble point.
Is when the vapor first forms.
Saturated vapor or liquid?
Is it vapor, ma'am?
Nope. It is a liquid. Okay. Why? First, sorry. I'm gonna close it. Okay, first, why is not a vapor? Okay, it is a bubble point. So the bubble point, sometimes also I confuse it between bubble point also dew point. In a bubble point, Pak Danu always remind us that the bubble point is what happened with my pen here? Okay, the bubble point is when we have a bucket of water, and then we heat it up, and then there's one tiny bubble coming in, so before it reaches vapor. Okay, so this is a bubble point. So this is we call a saturated vapor. Sorry, saturated liquid. Okay, and also this is called a bubble point liquid, so that means that is a saturated liquid. Later we really need to know our phase, because we have to know, because it is different, yeah, if we have the feed in saturated liquid, if we have the feed in saturated vapor, or we have the feed in a mixture between vapor and liquid, the outcome will be different. Okay, so from now we need to familiarize about the phase, yeah, of the feed. Okay, good. Okay, so then we have here we have a 55 pSAIA, about 620 a pound mole, and then this is the composition: 46 mole percent of benzene, and then 54 mole percent of toluene. First, benzene is written first, so that means which one is more volatile, benzene or toluene? Which one is more volatile? Mana yang lebih gampang menguap? Benzene or toluene?
Benzene, ma'am.
Yeah, okay, good. Benzene, yeah? Okay. Why there's, okay, need to check, okay, all of them here. Yeah, okay, so benzene is the A and toluene is the B. Okay, but if you want to still to put benzene toluene, it's fine, but when you write the first one is benzene and the second one is the toluene, so we know the convention that benzene is the more volatile. Okay, and then it is cooled down with the expansion valve here up to 19.25 pSAA. Yeah. Do you know what is the pressure? What is 1 atm convert to psi? 1 atm equal to how much psi? You can Google it.
14.7, ma'am.
14, yeah, 14.7. So that means this one is just a little bit of atmospheric pressure. Yeah. So it makes it makes to so the benzene and toluene easy to vaporize. Okay, so that's why when we have to also determine the pressure. For the pressure usually in atmospheric pressure or low pressure, yeah, or quite low pressure. But later when you learn about absorption, usually the pressure is higher, like 30 bar or something. Okay, good. Then it is put into like a split sides, yeah, the split of the tray. It is put it into tray 10, tray 13, and also tray 16. Yeah, if you look at here, the first one is called tray number 1, and the last one is tray number 25. Okay, so this is your duty later to calculate how much stages are in the distillation column. Okay, it is really so that is just, this is your basic exam. Yeah, you have to calculate, you have to be able to calculate how much stages of the distillation column. Okay, if you have a different feed, one is saturated vapor, one is saturated liquid, it will have a different outcome. Yeah, okay, and then here you have reboiler. Yeah, reboiler. It is called partial reboiler, where the partial reboiler, here you have full of liquid there, and from the liquid there it goes into a partial. Why partial? Because the output, one is in vapor, one is in liquid. Okay, so it's called partial reboiler. Okay, and then here you can see the pressure is slightly up, yeah, down there. So this is 19.25, this is 20.5 psa. Okay, and this is gonna be your bottom product, which is 98 mole percent of toluene at 251 Fahrenheit. right? And then you later on you also need to calculate the duty, yeah, how much is the heat that you need to vaporize those liquid, yeah. So the heat duty is 10 million BTU per hour. Okay, and then let's go back, go up, 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 up. All of the vapor here need to be cooled down in which one is this? This into like maybe a flash, yeah, or a reflux drum. Oh, sorry, should be cooled down into a condenser, yeah. This is called the total condenser. Why? Because all of the vapor, yeah, or the one that goes up is all vapor, no liquid at all on the top. Okay, and then should be cooled down 100% into a liquid. Okay, and then this is the heat duty, yeah. The amount of cooling water should be equal with 11,000, yeah, sorry, 11 million BTU per hour. Okay, and then here you have the L, or you have the reflux drum, yeah, and then you have a valve here, and then this also a pump, yeah, and this will tell you which one goes to the reflux and which one goes into the distillate. Okay, so then in the end you have for the distillate you have 623 pound mole per hour, with a composition of 99 mole of benzene at 169 Fahrenheit. Okay, so that means when you have here is the 620 pound per hour, you have also the distillate, and from the feed, which is only 46 more percent of benzene, you can enrich them into 99% of benzene. Okay, then that will require about 25 trays. Okay, so that is the introduction. So what is the fractionation column? So the fractionation column is the picture that I put into the picture in Edunex. So it's very tall and also quite thin, yeah. It's very thin. All right, let us continue. Okay, what is the factors that influence the design or analysis of binary distillation? First, so from those picture, you learn that it will include feed. Yeah, the feed flow rate, of course, will affect, and also the composition of the feed, and also temperature, pressure, and also the condition of the phase. Is it saturated liquid? Is it a saturated vapor? Is it a two phases? It depends. Okay, and also the degree separation between the two components. Yeah, first, for example, again, I know that in HYSYS a few years ago, when I try some of an example in HYSYS, they want to separate ethane and ethylene because they're really similar. So so it's very high, very low, yeah, the desired degree of separation between those two components. So then we end up with almost 99 stages, 99 stages of components. Okay, so but if the separation is between the two components that is has a high degree of separation, for example, I have methane, and then I have a little bit of maybe butane and pentane, just a little bit. Okay, so a lot of this degree of separation, I think the stages that we need is not as big as the before, yes, the ethylene and ethane and ethylene. Okay, and also the operating pressure must be below the critical pressure of the mixture, and also the pressure drop that also calculated particularly for vacuum operation. And then later on we're gonna learn about what is a minimum reflux ratio or actual reflux ratio later on, one by one. maybe tomorrow, and also the stages of equilibrium and also the actual stages. And then we're gonna also calculate all the accessories, yeah, the condenser, is it a total or partial or mixed condenser, and then the degree of subcooling of any liquid reflux, and then the reboiler, a partial or total, and then the tray later on. So what is the type of the stages, is it a tray or a packing? And also then later on in the after the designing, we know we can calculate the height and also the feed entry, also the diameter, and also the internal column. Okay, so this is a really a good exercise for you to learn about the real design chemical engineering. All right. Okay, so based on those example, let me explain about the so what is this, what is that? Okay, so here we have the feed. Okay, the feed is called the light key mole fraction is Z, we call it Z. Okay, and then the top stage is, we put it here in number 1. It's a little bit hard. Okay, and then this is the feed stage, and then here is the bottom stage. Yeah, so N is the bottom stage. Okay, the top side is called the rectifying stage or the enriching stages. The bottom side is called a stripping section. Okay, and then again it is put it into a total condenser. In the total condenser you have vapor, and then all of the vapor is gonna be cooled down until all of them become the liquid. Yeah, and then you have a reflux drum again to put some of them into, goes back into here, and this one is still up there. Okay, and then here at the bottom stage you have a partial reboiler, because you have vapor, and then you have you have liquid over here, and then there is a vapor there, and then you have also the bottom product also liquid. All right, okay, up to here, do you have any questions, or is there a particular section that you would like to be explained again? No? Okay. Right. Now let's check this the next one. Okay. Yeah. So what we're gonna focus in this class is to design is a design problem. Okay. So we know the feed condition, we know distillate composition, and then we want to calculate the number of substages and also the number of bottom stages. Okay, so this is called the process design. Later on, in your maybe group assignments with 2 of your friends, you will do equipment design. For example, the tray column design, which is you need to calculate the spacing between the tray configuration, and also the diameter of the column. The diameter will change if your feed is changed. Yeah, so if you have a large feed or a very small feed, and then the column diameter gonna change. But if you're in a master degree, or if you're in the plant, the chemical plant, and then you're in day-to-day operation, yeah, what you want to do is a problem solving. Okay, what happen if the feed is changed but the distillation column is just stay there? Yeah, what happen is the if we, for example, the I don't know, the amount of the feed is changed. What happened is the one tray is broken, so the stage is becoming less and less, for example, and then you want to have a good distillate product. So which variables that we need to adjust? So that is the problem solving. Okay, but in our class we're gonna focus on the process design, right? Okay, so let's go back. Let's start from here. Okay, here the total and the component mass balance. Yeah, first you have the feed. Yeah, so this is really, okay, I'm gonna put it here. So this is actually a really mass and component balance. Yeah, look at this envelope. What is it? I think there's something wrong with my pen. In the morning it's fine. I think it's too much on the computer. Okay, maybe sorry. Maybe just put wait. I'm just gonna put my cursor, yeah. Okay. Oops. Okay, let's share it again. Yeah, this one. Okay, see here. Yeah. Why is let me check one more time. Okay. I don't know why this happened. Okay, still stop it again. Just wait it. Or maybe I'm just gonna close the ini ya, the what is there? I think I'm just gonna close the PPT. Okay, wait a little bit. Okay, this one. Can you see it? Can you see it now? Hello?
Yes, ma'am, but it is not in full screen.
Yeah. I put it. How about if I put it full screen? Can you see it now?
Yes, ma'am.
Okay, good. So this one's better. Okay, so let's put the total and component balance first. Let's make an envelope. Yeah, between here, there. Okay, so in equal to out. Yeah, the feed in equal to the stream in equal to the stream out. The one that in is the feed, so this is the F. Yeah, and also the output of this envelope is D and B. Okay, so this is the total mass balance. And then let's check about the component balance. For example, this is the ZF of the component A, for example. So this is the Z is the mole fraction. So mole fraction in the feed of A, for example, multiply with the feed, yeah, that's equal to the component in the distillate, which is a mole fraction of the distillate multiply with the distillate plus the mole fraction in the bottom multiply with the amount of the bottom. Okay, usually this is FD and B is a molar rate, so usually we if it is in kilogram per hour or in liter per hour, we have to change it into molar. Yeah, usually it is in the molar. Okay, so that is the first is the total component balance. Okay, now how to define which pressure condition we can't put we really can't to putting any pressure in the condition because the pressure condition is really correlated into the condenser. Okay, so let's say if you have an atmospheric pressure of the distillation column, what is the typical cooling water in atmospheric pressure? The typical cooling water?
25 degrees Celsius.
Yeah, maybe 25, yeah. Okay. And okay. So then you I think now you're also learning SU, yeah, system utilitas, yeah. In system utilitas now also you will learn how much it can actually rise. Of course you can't rise it into maybe 40 or 50, yeah. Maybe you can rise it only maybe 35. Okay. So then you will learn later in a cooling water, yeah, in a heat exchanger. What is the typical the delta T over here, the minimum? Maybe sometimes 10 degree, yeah, sometimes only 5 degree, maybe the maximum. So maybe so this is so your T1, it should be that one there, or and this one maybe I don't know how much, yeah, maybe for example 32 for example. Okay, so this T1 is actually this one, yeah. So the T1 is what is this? It's in the T here, is this the vapor or liquid over here? The one goes up.
Vapor, Bu.
Yeah, vapor, good. So now the question is you have to check about what is the component, okay, and then check what is the and then also it will have a composition, and then at around this temperature, for example at around 45 degree, check is the pressure when it goes into saturated vapor. Okay, so you have to ensure that the pressure condition should allow the vapor will go into the vapor phase at, for example, 45 degree. Okay, so that's why the pressure condition would be always depend on the mixture, yeah, A and B. Maybe if you have methane and ethane, yeah, of course the pressure condition would be different if we want to separate acetone and ethanol, for example. Okay, so it really depends on how, if we want to use cooling water. Why cooling water? Because it's the most economical. We can get a lot of water, and then maybe from the river or from the sea, okay, from the seawater, we can get a cooling water. But for example, for some special reason you want to have a, but I don't want cooling water, I have a supply of, I don't know, ethylene glycol, for example, for cooler purposes, yeah, more cooled. Yeah, maybe you can have a lower temperature here. For example, if in a cryogenic distillation to separate nitrogen and oxygen, of course they can't use cooling water. Yeah, it's too high. Maybe they use ethylene glycol and so on, and then the temperature is gonna change. Okay, so that is the how we define the pressure condition. Okay, and also how to get the product temperature. Yeah, once we know the pressure, we can construct the TXY diagram. Remember, yeah, from last week, once we have those tongue diagram, the lidah, yeah, and then we cut it at one certain pressure point, and then we can have a TXY diagram. Okay, so if the TF if the TF is the composition and the phase of the product is known, for example here, yeah, if the product is liquid, then we can get the here, this one is the vapor, yeah, uap. Okay, the lower line is the liquid, cair. Okay, so here, for example, you can get this is an example. If you know the composition of the distillate, yeah, if you know the composition of the distillate from the component A and B, you know the YD, yeah, the component of distillate, for example 99 purity or 98 purity, and then look at this TXY diagram, see the YD, this is the composition, go there and go to the upper one because it is a vapor, yeah, oops, sorry. And then those vapor is become the TD for the vapor atau uap, yeah, this one there. Okay, conversely, if you have X in the distillate, okay, so this is gonna be your distillate, yeah, temperature distillate. Okay, the liquid distillate. This is if you get the distillate on the, for example, on the vapor, and this is, for example, on the liquid. All right, so that is the introduction to the, fractionation, and then tomorrow we're gonna start looking at about the top section or the rectifying section or enrichment section. All right, so I'm gonna stop the screen, stop the recording.